All right, in the last video, we were talking about plate heaters and ovens and hair dryers and sprayers and perfume bottles. Wait, is this a science class? Well, yeah, it is. And guess what? These things are there just like blenders and hot dog rollers and grinders and everything else is involved in our lab too. I mean, we even got microwaves. Hello. We've got ovens and stovetops. Those are our drying ovens and those are our hot plates. And far as stovetops go, well, in this video, we're going to focus on a different aspect of HPTLC analysis and TLC analysis. And this is more what I would call instrumentation based, of course. So I'm going to find this with HPTLC. Mostly, that's where I'm going to find this. So HPTLC is going to involve a process, possibly if I need to use one. And I see the word density in here, right? So this word density, well, density is like how heavy. That's what most people think of most of the time, even though that's not really the proper definition. But they think of like heaviness, like how heavy is something? Oh gosh, this has got a real big density. It's going to be sinking. Oh no, this density is pretty light and fluffy. It's just going to float on top of the water. Well, it's not quite what's happening here with HPTLC. This word density is going to maybe talk about, I'm going to put in quotes, how heavy or / dark the bands are in HPTLC. This is a densitometry system. Densitometry is the idea that I can look at darkness of bands in order to do maybe some work that I wasn't able to do in the past. So densitometry, that is what this video is going to be all about. So this is the concept that, we can quantify. All right, we can quantify numbers and we can build calibration curves and we can make standards and we can get linear lines. Absolutely, that's what densitometry is all about. So it is the idea that when I apply a band onto a plate, if it is very weak, it will have a very light signal. And then if it's a little stronger, it will have a darker signal. Then if it's a little stronger, it will be much thicker, much deeper, much darker. And then I can see that on my plate. And the densitometry system will go in and it will look at the darkness of these bands and it can actually calculate an absorbance. So I want you to think of really a proper, I guess the best way to think about this is going to be a proper UV vis instrument. That's what a densitometer is all about, right? That's it. Nothing more. That's it. All right, so with that said, bands are going to be scanned. You can go through and you can pick out a proper nanometer of wavelength for these densitometers. And that wavelength is going to be something that is very specific, maybe to the component or to the components that you're looking for. So again, maybe 254 is not appropriate. Maybe 350 and 366 is not going to work for you. But maybe something like 273 does. Maybe 273 is the best appropriate nanometer for these samples that you want to analyze. If so, that is great. This densitometer will be able to scan things between 190 to 900 nanometers. Again, just like a UV vis instrument. Our UV vises normally go from 2 to 900 is what we've often said. 2 to 400 is UV. 4 to 900 is visible. This can go a little bit below 200. And you know what, folks? Our UV vises in our labs can go a little bit below 200 as well. We just don't do that very often. There's no need for it. So that's why I keep it a rounded, clean number, easier to remember, 200 to 900. Absolutely. So that's what these systems are. They are UV vis instruments that are attached to these HPTLC systems that will do some of the absorbance value readings for you based on the spots or the bands that it sees on your plate. The result here, once I do a densitometer read, the results here are going to be PPSD. Woo! I've got SD. Post-traumatic syndrome, PTSD from this class. That's what I've got. Okay, well, PPSD is peak profile. That's what the PP is, of course. Scanning densitometry. PPSD. It allows me to do quant work, and it also allows me to do qualitative work, of course. So qualitative work is the idea that I can see standards, I can match those to my sample, I know what's there as far as RFs go, so it does do that. Then it goes the next step further, and it turns into a UV vis instrument in a way where it's telling me how dark the bands are, so that way it gives me an absorbance readout, and I can change those absorbance readouts into calibration curves, and then I can solve for the unknown concentrations that's in the samples. That's what this is. That's what it's all about. It's what it's always been about. This is what HPTLC and TLC was missing up until this component and this module comes into play. So densiometers are very important. That word is very complicated to say. I don't know if you've tried to say it yourself or not, but it is kind of complicated. It's a little tricky. So very often they just call these systems the scanners. That seems to be a little bit easier. It rolls off the tongue a little bit better. And when we talk about scanners on HPTLC instrumentation, we know exactly what you're referring to. So we do use that. That is okay. But the proper term is the densiometer, or the, UV vis scan that's really happening. It's just a different way to call it a UV. All right, here's a scanner. Notice that KMag even calls it a scanner on the top. So KMag TLC scanner, this is version 3. This thing opens up again like a bread box. It's a little accordion door that folds down. You put your plate on the inside. The plate is going to line up to some guides. So how far do I push it back? How far to the left do I push it back? Very similar to the visualizer, because the visualizer is built that way as well. So the plate will go in, and I'll push the door back up, and then I allow the software to go through, and it will dial into a wavelength. And when it dials into that wavelength, it will kind of hang out there, and it knows what to look for. And then what it's doing is that it's scanning. That's exactly what it's doing. It's scanning the plate. So you're going to hear this plate kind of move around. So what you'll see is that this thing kind of moves back and forth and up and down, and then you'll hear it go boop, 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 boop. That's what it does. So there's my sound effect, my new one for the day. And then as it's doing that, what it's doing is it's gradually working itself up the plate, and then it's going from left to right on the plate as well. This is kind of an old school version of the scanner. Of course, it's been upgraded. This is kind of what the newer ones look today. Again, the door slides open. You paste the plate on the inside, close the door back, and then away you go. You can kind of do what you want to do after that moment. Type in your wavelength that you want to look, and then allow the instrument to go. So as it's doing that, it's collecting information. It's looking at where absorbance is taking place, and wherever absorbance is taking place, it is kind of making a mental picture of that as it's getting developed, and then it knows what's there, it knows how dark is there, and it can give you absorbance readouts on that as well. So if I take a look at just one lane, let's just take a look at one lane, right? So I'm going to come in, and we are going to draw a lane. And then let's say that I'll get a spot that's here, and I get a spot that's there. All right. And those are darker spots. At least the machine can see it. The scanner can see it. That's not a problem. All right. So what's going to happen is that the densiometer is going to start down here at the very bottom. And then when it does that, it's like a baseline. Nothing's getting absorbed, right? So nothing is getting absorbed at all. Then what goes on is that as the eyeball begins to, it is flatline, 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 flatline. And then it gets to an area where it's like, oh gosh, I see something. It's absorbing. I get an absorbance here. And that absorbance is going to make this graph go whoop and then come back down. And it's going to come back down because it's going to kind of stay up as it travels over the spot or over the band. And then when it goes back down to nothing, then it's going to go back down to baseline, and then it's going to draw flat areas all over again. So flat, 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 flat. And then it goes, there's something that's there. I'm going to absorb. And then it goes, and then whoop, and then it goes back down to baseline. So in the world of chromatography, folks, this is kind of like chromatography, and this is what HPLC would be doing too. It's a detector, and it's saying nothing, 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 and then, I see something coming out of the tunnel. Well, the same thing's happening here with the scanners. It's just not coming out of a tunnel. So what's happening is that the eyeballs are scanning the surface of the plate, and then when it sees that something is there and it's absorbing, it is letting you know that. And it's letting you know that by something that looks like, in a roundabout way, a chromatogram, which is why we're talking about this in a chromatography course. Wow, go figure. Well, here are some PPSD charts that you can see. So notice, though, that these are not very clean. This is not what I would call resolute. It's not what we would kind of typically refer to in the chromatography world. So there is a little bit of a slight difference. But what I do see are like peaks, and a peak, and something here, and something there, and something here, and something there, and something here, and something there, and something here. So that looks like it is finding multiple components. And these things could be very close together, which is why the baseline doesn't hit in between every single one. There's not enough time for it to do that. So while it's not a traditional chromatogram that has very good resolution, it looks similar to one. I see peaks that are there. I see stuff that's going on. Maybe my developing solvent is causing some absorbance as well, but at least I see different maximums, and I'm seeing different maximums, and that means, well, there's different components and there's different pieces of the sample that are present. So it is there in a roundabout way. It's not super clean, but I can think of it like a chromatogram. Also notice over here on the right-hand side, I see a big old blob, a big old blob, a big old blob, and a big old blob. Those normally are mobile phases. So it does see that sometimes as well. Our mobile phases can respond to some of the derivatizing agents or to some of the nanometers. So for instance, if I'm using acetone as part of the developing solvent, acetone has a UV vis absorbance. Just naturally, it has a UV vis absorbance. Absolutely, it does. So with or without a derivatizer, it does not matter. It's going to pick up that absorbance. It's going to showcase that on the PPSDs that I begin to see, or the peak profiles that I begin to see on these lanes. Also notice on the right-hand side, it's changing wavelengths. 254, it goes to 260. Look at what happens to the peaks. They become more distinct. It then goes to 316. Look at the peaks. They become more distinct. Look at the 350. Look at the peaks. They become more distinct. So we're getting more sensitive peaks, which means taller peaks, which means the separation I see a little bit easier concerning these different lanes and these components that are in those samples. So this is a peak profile. This is what we refer to that as. We do not call it a chromatogram per se, but we call them peak profiles. Every lane will have a peak profile. And that peak profile is coming and getting originated from the multiple components that are inside of your sample that you have an analysis run of. If I was doing a standard, a clean standard, guess what? I would see a that would be it, because only one thing should be there. It's a standard. Only one RF should be present because it's a standard. It's super clean. It's not contaminated, and therefore I should only see one peak. That makes it very easy to figure out what my RF is supposed to be. And then from these graphs, from the peak profiles, I can say this is the peak that I want. This is the RF that I want. I want to know what is the absorbance at that location, please. And then it will tell me. All right, so that is the mode. Just like with UVs, they are absorbance based. It's absorbing the UV light. It is eating that up, and that makes those bands darker on the plate according to the eyeballs of the machine. And therefore, I can get absorbance values, and then I can take that absorbance value and I can plot it onto a calibration curve. Absolutely. That's exactly why we would use a densiometer. So as I make my standards, my absorbance is going to go up and up and up. Just as before, I can get a y equals mx plus b. I can then take an absorbance from a sample component that I'm after. That absorbance is probably plotted in for y if they do the traditional linear regression line. So I'm going to take the absorbance, plug it in for y, and I'm going to solve for x and X will be the concentration of that component within the sample that I've ran and that I've analyzed. Absorption, just in case you've not taken the spectroscopy class before, it is the idea that the light beam is going to be directed onto a sample component, and that sample, of course, is going to be on a plate. That's what you're seeing here. That's the blue bar. So the light source is going to have all of my nanometers that I can choose from. Anything's appropriate for that light bulb. It's going to go through a monochromator. The purpose of the monochromator is to pick out 1 nanometer only. That is it. It kind of fine tunes it, gets out all the other noise. So I want 355, please. I'm going to type in 355. It only shines 355 onto the sample. And then as it sends that 1 nanometer that I have selected, a couple of mirrors in here are going to bounce. It goes onto the surface of the plate, and it begins to kind of pick up where things are going to be located. So here in the beginning, on the top half of the picture, you're seeing that light beam, that 366 nanometer, it's not really coming in contact with anything at all. That is just the plate, the silica, nothing special. So that's just straight up, nothing's getting absorbed. Nothing's getting absorbed. Everything is getting through the detector, and it tells me that on the peak profile. As it begins to scan further and further and further down the plate, then it gets to the band, it gets to the spot, and then alert, 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 you got something, you got something. So what you're seeing here is a little bit of the light that's escaping through, reaching the detector, and if you looked up here, it's a whole lot of the light that's coming through because nothing absorbed it. So that sample is going to absorb that light just like it did in UV vises, and if you've taken spectroscopy, partial of the light will go through, partial of the light will reach the detector, and that detector will tell me how much actually reached that moment. That is what that is all about. So that is the peak profile. That is the purpose of a densitometer. That is how the system works, and that's what this is all about. Okay, so that's absorption. And in the next video, we're going to talk about another version of this, and it's fluorescence. We didn't really talk about that too much, I don't think, in the spectroscopy course, but I do want to talk about fluorescence and how this is a little bit different. So in the next one, that's where we're going to pick up, and then we'll finish out the densitometer, and that will probably finish out the material on this assignment that these videos are related to. So come back. We got one more video left, probably in this assignment, personal video, if I didn't change my mind and cram in more things in the future years, but we'll see how this goes, and we'll pick up from there. So fluorescence is on the table, folks.